We're looking at a Windows Server 2019 HPE ProLiant system. It's operating inside the Microsoft Mega Lab data center, located in Building 88, on Redmond campus in Washington State. The desktop taskbar at bottom includes a display of current time and date at its far right end. This display is updated every 60 seconds, at the top of the minute. A running stopwatch is added above it, as a visual aid, affirming this recording is unedited. The wall clock above it is a 5-year-old Windows Classic desktop app. It is showing the current time of day, according to the operating systems. The control panel, at the upper right corner of the screen, allows an authorized user to set time and date, and timekeeping methods on this system. The system administrator, or an authorized user, can also change the current time of day on this system, using command line interface. That's what I'll do next using the classic command window, on the left-hand side of the screen. I'm using the time command to force time of day on this system to an incorrect one. Let's try 34 minutes after noon. Did you catch what the system was doing? How about 15 minutes before midnight? But before I press the return key, I want you to focus on one of the time displays on the right-hand side of the screen. Perhaps the wall clock is the easiest one. Ready? Sorry, I forgot to show you earlier. The date and time control panel indicates the system is not relying on network-based time synchronization. Instead, this is a sync and scale-enabled HPE ProLiant server. So, what just happened? I entered a valid command. The system accepted and acted on it, as it should. However, immediately, the Windows Server OS kernel was also informed by sync and scale that the system had been forced into an incorrect time of day. The kernel took remedial steps to discipline the system clock and brought it back to UTC accuracy. These were reflected by the desktop apps when their displays were updated at the next second boundary. This cooperating interaction between OS kernel and sync and scale system interface happens several times per second to keep system clock persistently UTC accurate. The same interface also delivers GPS geographic location information to the system continuously. This Windows desktop app displays GPS-originated geographic coordinates and corresponding time zone, as well as current system date and time, and its cyberspace time zone. Business needs, or IT rationales, may dictate UTC as the configured system time zone for all systems making up a solution platform, regardless where they operate geographically. I am now making that change on this system, in its date and time control panel. A sync and scale-enabled system provides its true geographic location information, separate from its cyberspace time zone. These two sets of complementary data points allow it to be more versatile and capable for modern IT solutions. The command line app SNS GeoStamp is a sample reference tool. It exploits these building blocks on a persistently UTC-accurate system to construct trusted time and place markers. These markers are conforming to the CCT specification. This command creates 3 consecutive geostamps, 5 seconds apart. Accuracy of a geostamp is authentic and can be trusted when the functional integrity of its issuing platform is verifiably definitive and persistent, and data used for its construction are coming through operationally known secure paths.